Howdy, my name is Wesley Palmer. I'm going to talk to you all a little bit about unmanned aerial vehicles for forest applications. My main area of study is GIS, remote sensing, GPS, the geospatial realm. Does this guy work? Okay. So what we're talking about is drones, or unmanned aerial vehicles, or UAS, unmanned aerial systems. You'll see SUAS, small unmanned aerial systems. And there's a wide variety of platforms out there that are available that fall under this category, right? There's the ones that the military uses that shoot missiles and blow stuff up. There's small toys, that you might buy for your child at Christmas. Then there's everything else in between. There's multi-rotor platforms. So there's like the one that I flew in today. There are small helicopters, that use change in thrust on different axes to change direction. And then there's fixed wing platforms, like some of the ones you see up here that just rely on a fixed wing to provide lift and then a motor to go forward. So there's a wide variety of drones out there. The ones that I'm going to be talking about that I have the most experience with is the multi-rotors, right? So the ones that you see up here. One thing to consider is the FAA is going to be should be December 22nd is the date. Sometime this month they'll be releasing the rules for commercial use for this type of technology. And those rules will be the SUAS rules, or the small unmanned aerial systems rules, which means 55 pounds or under. They're going to try to integrate small systems first before the big ones. All right. So I want to talk about data collection and how we can use that data in our management decisions or our GIS operations. Historically, we've used manned aircraft or maybe satellites orbiting above to collect this data. So an airplane, flying with a LiDAR scanner in it, and scanning the ground, giving us very accurate three-dimensional elevation information. And then, or we'll have an airplane with a camera on it, and it's collecting aerial photography. So, it flies forward and collects different aerial frames, or maybe it's a photography scanner, and then we can use that data for GIS-based maps and things like that. What's sort of exciting about the advancement of this technology is we're still using that same type of data, right? But what we're able to do is put that data collection capability in the hands of a small consulting forester, right? So we don't have to pay $5,000, $10,000, $20,000, $50,000, $100,000 to collect, to hire a company to go and collect a aerial data set. For smaller areas, we can do that ourselves, and for the low cost of some of these things, you can buy a system and implement it and be able to produce professional quality data for a relatively low cost. Which that's what's gotten me excited about the potentials of this technology. So, with these multi-rotors, they've got a pretty good lift capability. So we can lift a laser LiDAR scanner here, a very small one. You can integrate a camera on there so you can get LiDAR and aerial photography on the same platform. Or you can just mount a camera on there with a gyro-stabilized gimbal so the camera stays steady as you're flying. So this is sort of these same systems are in airplanes and helicopters that are manned systems, and we're moving those systems to unmanned platforms. All right. So let's look at some data that we might be used to seeing. So in our GIS operations, we might have an aerial photograph background, a base map. So we can zoom into a track and look in an area. This is a road and part of a golf course just to see some features that are there. Then we can do stand delineation here. We can use some classification and look at species information. We can do a lot with our aerial photography resources. Then with our LiDAR information, a lot of us might, who use GIS and you use a LiDAR to look at elevation and contours of a certain track, you might go to the Atlas website and download some of that LiDAR data, or maybe you have in-house LiDAR in your company, and you might just be used to the digital elevation model, right? Or just the terrain, just the ground level. But with our three-dimensional data, we can extract out all sorts of information from that 3D point cloud. We can create contour lines. We can create a digital surface model. So now this is not just the ground, but it's everything that exists. And this is more interesting for us because we have trees and we have heights of trees. heights of everything that's there. We can do a hill shade model to sort of help visualize what the surface looks like. And what that hill shade model is it models the position of the sun at one time and sort of models those shadows, so you get that that sort of hill shade look. If you repeat that hill shade for every time of the day, or let's say every 5 minutes of the day, and then you can then calculate the amount of hours of sunlight exists in a certain area, and then create a sun exposure model. And so here, the red areas have more sunlight, and the blue areas have less. And this could even be done, to maybe look at how much sunlight is going to hit the canopy floor. This type of analysis could be used for that purpose. So there's a wide variety of products that we can produce with LiDAR and aerial photography. With our three-dimensional point cloud, so on the top here, that's a three-dimensional LiDAR point cloud. It's a little profile view of a forest stand. We've written some software where it'll go through and it'll look at the peaks of the crown of each tree, and find the highest point on that crown, and then get that elevation and then assign that as a tree. And so we can place a point on top of each tree that exists out in the tract, and then also calculate the height of that point from the ground surface, from our ground there, so we can get the height of that tree from the ground to the highest return that exists there. So that can help with forest inventory. If you're just looking for trees per acre, you can get a 100% cruise on a large area of land fairly quickly with some automated software. So all these exciting things that we can do with data, instead of having the large expense of paying a manned company to go up and fly, and maybe we only have that 40-acre tract, we can use these tools to produce the same or similar type data ourselves. So what's made this more possible recently is the technology. We have smaller and more affordable inertial measurement units, so the accelerometers and gyroscopes that are inside of the drones that measure which way it's facing so it can correct itself and be stable. Battery size, so we're getting smaller and smaller batteries with higher and higher voltage rates and capacities. And so the cost as well. So all the data that all the three-dimensional data that I'm going to show you collected from the drone today is all collected from the little white one, the DJI Phantom. So the smaller one here, that is, so the DJI Phantom costs around $800, and then the GoPro camera that's on it is about $400. This is not the optimum aerial data collection tool. But the data that I'm going to show you was produced from this setup. And what we're looking at doing is we're now going to be testing other more advanced sensors designed for this to really enhance the data that we're looking at. So for potential $1,200, you can have a data collection tool that can produce some actionable data for us. And so I think that'll, and then once you buy it, the only additional expense is charging up the battery and then going out and flying it again. All right. And then they're relatively easy to use. So you don't need a simulator to learn how to use it. It's pretty simple. You pick it up, you fly it, you're off and ready. And I want to introduce these guys. So the smaller one is the DJI Phantom. The larger one, I guess you would call it a DJI F550, but it's really more of a custom build. That's one that I built myself, and I got parts and pieces from different places. I built that one. So I know I'm not supposed to step away from the podium here, but with these batteries, if I load up 2 of these batteries, I can hover it for about 55 minutes on 2 of those batteries. Flying with 1 battery and then the payload that I'm going to put on it to enhance our data collection techniques, I can fly for about 18 minutes doing quarter mile back and forth sprints at about 20 miles an hour. So you can cover, with that platform, you can cover maybe 100 acres, 150 acres, in one flight of data collection. So that's sort of the size of an area that you want to look at. Some of the fixed-wing platforms can fly for even longer and higher and faster, and they may be better suited for larger areas. What's nice about these smaller multi-rotor platforms is they're really easy to fly, and you can handle them yourselves, and you can test things or whatever. Whereas the fixed wings, they take off and they're gone, and they're sort of flying themselves, and they're difficult to control sometimes. Whereas these, you can hover it, indoors, with just a little bit of practice. All right. Another function of these is you can have autonomous flight, or it has an autopilot that you can set up. So here's a little screen grab of the flight planning software. And so you would pick an area, say, all right, I want to fly this track, and you'd say, I want to fly it at this altitude, at this speed, I want this many flight lines. If you're unsure what those parameters might be, there's another module in there where you can say, I just want this ground resolution of photography. You calculate it for me, and it'll go through and calculate the flight lines of what that flight needs to be. Then you upload that flight plan, so those waypoints and that track, to the device. You can do it while it's flying on the go. You just hit upload, and your computer transmits it to the device, and then you hit go, and then it goes from manual control to automatic control, and then it'll go and fly those flight lines. And then when it gets done, it'll return home and land, or you can take control of it and send it on another flight plan. So this is also very important because it's difficult to fly in a straight line consistently, right? So if you're watching it and it's like 100 foot up and you're trying to fly it in a straight line, just down this fence line and then over 50 feet and come back, kind of like mowing the lawn, it's difficult when you're watching it. So when it can fly itself, it's very, very useful. Okay. So some applications. What can we use this for, right? So if we think about what do we already use our aerial photography and LiDAR data for, right? So all of those things, maybe plus a little bit more. So there's some unique things that we can do because we're closer to the ground and we can get higher resolutions. So we can create orthomosaics, right? So a base map for our GIS and an updated one, right? So right now you might be looking at the 2012 imagery that you have in-house. But if you want, December, what's the date? 12th, 2014, you can go out and get it and have it that day. And if you want the next day, you can go get it the next day, maybe a before and after, a clear cut for minimal cost, just sending a guy out there to go collect it and then come back. So having that to be able to update your data and have recent data is useful. With different cameras and different lenses, we can look at we can bring in not only the red, green, and blue, but the near infrared band, look at the normalized difference vegetation index to look at some plant vigor and crop productivity. They have functionality where it's called first-person view, but basically you can look at a monitor. So some have monitors, some have goggles that you can wear. And let's say that you need to go, there was just a clear cut and you want to go inspect that track, just visually. And it's a 300-acre track and you forgot your four-wheeler and it's wet out there. You can put on goggles or look at the monitor and sit inside your truck and fly that up, and then you'll be seeing or looking at what that camera is looking at in a live real-time feed. So you can just go look around, fly around, go check out things. Maybe they left a few logs here or there, check everything out, and then fly on back without having to go there. So yeah, I have a ceiling survival example that we'll look at from collecting high-resolution aerial photography. Again, using your orthomosaic to do some image classification to look at species. And then kind of another cool portion of that is the photogrammetric point cloud. So the idea is traditional photogrammetry, when you have a photo of the same area from different angles, you can then calculate not only the X and Y position, but also the Z position, or the three-dimensional position of each pixel that exists in that photo pair or that photo frame. Here we're going to use multiple photos of one area to get a really accurate three-dimensional model, and we'll look at some of those. From there, we can look at the crowns of each of the stand, and then count. Use our tree identification to say there's a tree, and measure height. And then from there, you can look at stand density. We can look at crown shape, and then I also have a little example of maybe looking at tree diameter from flying them. Not over the canopy, but through the woods, I guess. To Grandma's house we go. All right. So here's a ceiling survival example. And this is sort of a really nice test area. It's a mowed field out on the Louisiana Tech Farm with some one-year-old loblolly pines out there that another professor had for a project that he was doing. Let me turn this guy off. So I flew probably about 100 feet, and the ground resolution of this is about 2.5 centimeters per pixel, so we have very good resolution. And because of the study, some of these trees were shin high, and then maybe some of them are waist high to get an idea of the size. But you can clearly see each individual seedling in the image. From there, we can run it through some image classification and pick out what's a tree and what's not a tree, right? And so the green areas is what we classified as a tree. And then what we do is we basically get rid of everything that's not green and just take those tree classification pixels and then find the centroid of each individual group and then place an XYZ point on top of each one of those centroids. So you then have a GPS coordinate, a geographic coordinate of the center of each planted tree that exists out there. And so this could be useful for identifying gaps or looking at seedling survival or having an accurate count of exactly how many seedlings exist after 1 year's time, and then be able to say, all right, maybe we need to put some more out there or evaluate whatever you need to look at with seedling survival. I'm not a practicing forester. I deal more with the GIS stuff, so you guys can tell me more about how you can use this versus examples that I can come up with. All right, so that's our seedling survival using just high resolution aerial photography. And this can be something that can be done, you can go out and just fly individual sites and come back, process the data, and then produce these results. So to take a look at some 3D photogrammetric point clouds. So here we're looking at pixels that have been turned into XYZ points. So everything we're looking at is just a collection of individual X, Y, and Z points that are geographically referenced. So they're spatially accurate points. So this is just a picture from the Phantom of a stand that Dr. Mike Blazer let us fly. And there we are down there at the bottom. And then here's sort of a rotated view of the 3D photogrammetric point cloud of that same stand. And all of these examples are just sort of first tries with just this little consumer grade device. Also, you can see those little flags. Those are ground control points. Those are GPS points that we took on the ground and then registered to this point cloud. So I'm going to kind of rotate it around a little bit. And so you can see, you can kind of see the trees are sticking up there. You can see where those points are. Here's sort of a backwards view where you can kind of see each row there and each canopy. And this, the points that we got in this canopy, I would consider not good enough. We need to do some more iterations with some better camera data. But still, you'd be able to get fairly accurate heights of each one of those trees. The difficulty is separating out each tree because the way that this software works, it sort of made it nebulous as far as where the peaks were. So we got to refine some things there. But this was just a first run, just a little play test trial, and it turned out pretty well. All right, there's a picture of the ground control point. So what we did was we painted a little X on the ground, and then went out and took a GPS position of that X. Then we can register that X with the three-dimensional point cloud. So the point cloud then becomes as accurate as your GPS data. So if you've got survey grade GPS data and you're accurate to a centimeter, your entire point cloud is now as accurate as that geographically, down to a centimeter accuracy. If you do not put down ground control, your point cloud will still be relatively extremely accurate, right? So from the ground to the top of the tree, it's very accurate. But then if you bring that data into your GIS, maybe the whole thing might be shifted spatially 3 or 4 feet, right? So to get that absolute geographic accuracy, you can bring in ground control and then produce those better results geographically. Here's just, instead of looking at trees, we're sort of looking at Lomax Hall. Those folks who have been to Louisiana Tech School of Forestry, I've seen that building before. And so you can see, and remember, these are individual 3D points, but there's so many of them that it looks like a continuous surface. I'll sort of rotate around there so we can see, how well it mimics the shape and size of that platform. And so we can measure anything from any one point to any other point within this surface. We can measure tree height, we can measure the width of that building, the height of the building, and there's also some ground control in here as well. So yes, here's an example. We took, and so this is kind of zoomed in. You can almost sort of see the spaces between the pixels in this shot, but we took GPS points on the 4 corners of a little ramp there that goes into the parking lot, and also measured it with a tape measure. It's 14 feet on the ground. It's also 14 feet exactly within the point cloud. We also measured heights of walls and different things, and all of our ground measurements were exact within a few centimeters of what our point cloud represented. So we can create really, really accurate data, which is exciting, with a very low-cost solution. So here's a just sort of how you can get crown shape. This is a I don't even know what type of tree this is. It's on the way to Bill Patterson. What type of tree is this? It's the one that's on the way. Looks like a Christmas tree from Lomax to Resall. Yeah, so it's some sort of ornamental tree. It looks like a little Christmas tree out there. Anyways, you can see the shape, of how well it captures what's there, and so we can reproduce this same shape of whatever exists there, exists in the forest. All right, let's look at our tree diameter example. So this is an old shade house. It's on the west end of Lomax Hall. This is a picture of it, and you can see this is my regular test forest, right? We've got telephone poles with no branches, no vines, no obstacles, but they're nice rows for us to sort of test and work with. So what I did here is I took the little Phantom and flew sort of a zigzag pattern, about halfway up the pole, right, and had the camera facing horizontally. So I was taking pictures. So this picture was taken with the drone as it was flying back and forth in between those rows. Then, because we have pictures from both sides of that those poles, we can then reconstruct the exact three-dimensional shape, size, and dimension of what's there. And so here's a look at the 3D photogrammetric point cloud of those poles, and you can see that there's a little bit of noise there. Those white little flurries are erroneous points. Those are not correct, and so there's some refinement that can be done with this technique for sure, and that's going to come from using a better camera. So here's sort of a zoomed in look. You can see the individual points there, and you can see the detail of, it's capturing every little bump and every nook and cranny that's on that pole is captured from that three-dimension that point cloud. Here's just a different look at the base of the poles, sort of rotating around, looking at the other side there. Here's a look. I've sort of moved the point cloud, so we're looking as if the pole was hollow and you were looking down to the ground, right? So here is the volume, right? Here's the space that pole occupies, and we have points basically every few inches around the entire stem or the entire body of that pole. So we can calculate the complete volume of this pole, right, from bottom to top, and instead of measuring dBH and height and then estimating what the volume is, we can calculate the exact volume of every pole that exists, within our data set. And so that's something to look at. But for comparison's sake, what I did was I took a horizontal slice of the photogrammetric point cloud. I took about a 6-inch slice at about dBH height. And then I also had a graduate student go out and then hand measure each one of the poles as well. So here is, in a top-down view, each one of the sort of cookies or the little rings of points from that 6-inch slice that I took of elevation. Zoomed into one of those areas, so this is what that that cookie or that profile view of that slice would look like, right? And so you can see that there's some noise in there. Right? There's a little bit of noise, but roughly we've captured the shape of that pole. So with some GIS magic, we can fit a circle into that collection of points. And as I was doing this, I was making sure that every step that I did, I could do it in automated fashion. So if I had to do 1,000 of these or 10 of them, it would take the same amount of effort for me. I could just give it to the programmer and let it do what it's going to do and spit this out. Then we can calculate our diameter from that collection of points. So this table is just sort of a comparison of what we calculated from the photogrammetric point cloud and what was measured on the ground by the graduate student. And so we're off by a few centimeters, sort of on average there. But it was some pretty optimistic results for just a wild guess first try on let's see how well we can do with this technology. So here's sort of an idea that I have in my head, and I'm not sure if it'll ever happen or not. But we're working with some folks in engineering on being able to fly these platforms cooperatively so that they will communicate with each other as far as where they need to be flying. We have flight controllers now where we can set up multiple platforms in a formation and then fly the whole formation. We have technology now where we can tell the smaller drone to follow the leader, and so I fly the bigger one, and then the smaller one follows it. And you can do that not at the same altitude, but you can offset altitudes. So there's also technology being developed. There's a few papers that are out on collision avoidance. So they'll put small sonic sensors and small LiDAR sensors and small image sensors on these platforms so that you can fly it in one direction, and if there is an obstacle, it'll see that obstacle, sense it, recalculate its trajectory to go around it or above it or below it, and then continue back on that track that it was at. So potentially, I can see where you would be commanding a swarm of drones and telling them to basically go cruise for you and fly them into the canopy. They'll calculate your height, your diameter. One can fly above, take photographs, calculate your species, and then be able to process all that data back in house and end up with a 100% inventory of what exists. It's sort of a futuristic, optimistic idea. However, I'm seeing a lot of different pieces of this puzzle coming together in the next few years, so it may not be so futuristic after all. We'll have to see. So yeah, so that's, I'm sure there's going to be a few questions. I was doing some payload testing at my house. Turns out 2 Coronas is the exact weight of the camera and gimbal that I want to get, and so it worked out pretty well. So the whole thing with this is weight, right? So you want to have all your weight. The less weight that you have on there, the longer flight time that you could have. So if I had that, so each one of those bigger motors produces 600 grams of thrust at 50% power at hover. So I have 600 grams times 6. That's the maximum amount of weight that I can carry with that motor configuration. So if if I had the least amount of weight, the smallest camera, the smallest battery that would produce the most amount of energy, that's what's going to influence my flight time and to be able to fly for 2 hours, 3 hours, 4 hours, and just have it going. If it could fly for a longer period of time, you wouldn't even have to drive to the site, right? They can do 40 miles an hour, and so you could just take it off from your office and send it to go collect the stand and then fly back and give me the data. But right now you have to at least drive out there and then fly it once you're there. So. Solar powered wings. They're making one called the Department of Defense is making one of those. So one that can stay aloft for like years at a time. It's called like the solar wing or something like that. And they're putting wide area persistent stare platforms on those to be able to stay over, the Middle East for ever, and just cruise around using solar technology. But that's a fixed wing, which uses lift, and they use a small amount of energy. Is the battery on the drone? So this battery goes on top here. I Velcro it down. So this would be battery and drone configuration.
What's your vertical limitation?
Physically or by the FAA? Right. So physically, you're going to be limited by your remote control range, right? So once you get out of communication range to the drone, they have fail-safes in there where they'll stop and then fly back to where they took off. And so your line of sight range, mile and a half, around there. What you would do is you could fly lower, maybe at like 100 feet. But what you're doing is you're taking a series of pictures. And then when you get back, you're mosaicing all those pictures together to create one big picture of the whole area. So that way you can fly lower, get really high resolution individual images, and then when you mosaic them all together, then you have that one big picture of the whole track. Now you could fly up to an altitude where you can get the whole track in one picture, but then your resolution has suffered and you can't see all the detail that you'd want. So they can make a version of this with an attachment where you can use your iPhone as the flight planning software, and you can see on a little Google map, where it's going, or you can also, they have some other systems that it transmits the video feed to your iPhone. Yeah, and so you're able to watch the video and then fly as if, you know, your eyes were here instead of having to watch it. So yeah, that's they make like 3 versions of this thing, and so that's just one of those. I think it's called the Phantom Vision or something like that. Just one of those versions. So what I see happening is, you know, they're going to need to develop some sort of driver's license for these things and some sort of registration process so they know what's going around in the airspace. And so I could see them coming up with a UAS certificate. So it's some sort of credential where you have to, there's a workbook and you have to do some studying and reading and knowing the rules and regulations, what you have to do, take some online test or go to a testing center, take that test and then get your certificate, and then you can be a commercial operator or whatever. But yeah, there's been some concern that overregulation of this technology can stifle the innovation potential that's there by the commercial sector because of all the potential applications, not just within the natural resource or remote sensing, but in, you know, package delivery or my mother is a nurse, and I was talking about it with her, and there's 2 hospitals that are near each other that transport blood back and forth for whatever patients they have. Well, there's traffic jams, and, you know, they have couriers that get stuck or whatever, but I can put 2 pints of blood on this thing and have it, you know, from here to there in automated fashion, taking off and landing, you know, in 3 or 4 minutes to travel a few miles. So technologies like that, you know, applications are sort of endless for this technology. So hopefully they make it so we can use this stuff. Yeah.
What type of software are you using to remove the fisheye effect off your cameras and generate your 3D content?
So for the fisheye effect, it's a software called PT Lens. It's sort of a small package. I think it's like $30. It's this guy wrote it, and so you can visually sort of adjust settings to remove that barrel effect, and then get it set, and then go from there. However, to your next question, which software for the photogrammetric point cloud, Agisoft PhotoScan and Pix4D are the 2 software packages that I'm testing and working with. They both have their merits as far as some do some things better, some do things worse. But I believe that Pix4D already has a built-in camera calibration model for a GoPro, so it takes care of that barrel effect for you, and you don't have to pre-process the images before you bring it into that software package. Someone have another question? No. Yeah.
Does it have terrain following capabilities? Because if you're going to try flying at DVH, you got hilly terrain.
Right. So for that application, you wouldn't need to fly at DVH height. You would just need to fly in sight of the bottom and the top of the tree. So you could sort of be up or down as long as it's within the field of view of the camera. But terrain following is important for if you're doing an overflight and you want to maintain a consistent ground resolution, right? Because if you're flying at a fixed elevation, but you're on the side of a hill, you're going to have lower resolution here or higher resolution here. So these platforms, no, they do not have terrain following capability. You would have to, in the flight planning software, adjust your altitude of your waypoints. And so you could build that into the flight plan and say, I want you to fly from up here in a straight line down to here and make sure that's consistent offset.
Build it into it, but it doesn't have the automatic capability.
Right. These do not. There's one that we just put on order called the DJI Inspire 1 that on the bottom of it, it has 2 sonic sensors and then 1 image stabilization sensor. Now, what it uses that for, it is not terrain following, but while it's indoors. So these use GPS while they're outside to maintain a stable position. But inside, I couldn't just let that one hover. I had to actively control it because it doesn't know that it has moved left or right, and I have to tell it. Whereas when it's outside, it follows a GPS position. It will just stay at that spot if I do nothing. But that technology on this new drone is, so it's using sonar like a bat to get a range from the ground, and then it's got a camera on the bottom, not its payload camera, but a small camera that uses computer vision and basically looks for the lines in the tile or anything that's on the ground, a spot. And then as the drone moves, that spot's going to move in that image, and it knows that it's moved, and then it corrects to put that spot back in line with where it's supposed to be on its initial fix. So it's using those technologies. So for terrain following, that sonic capability only has a certain amount of range. So you would want to use an active technology like a little LiDAR scanner to ping the ground and then get your range so it could adjust for that. But all those technologies are being developed and are on drones, but are being used for slightly different purposes. And so it's just a matter of time before someone says, let's turn it this way and use it for that purpose instead of something else.